All right, let's dive into something that sounds, well, completely backwards. We're going to explore a really beautiful paradox. How can pure, total chaos and randomness give us one of the most precise fundamental numbers in all of mathematics?
I mean, really think about that. It just shouldn't work, right? It feels like saying you could figure out the exact recipe for a cake by just randomly throwing ingredients into a bowl. But what if you could? The answer to how this works is actually, believe it or not, incredibly simple and elegant.
And the solution to this puzzle has a name that, honestly, couldn't be more perfect. It's borrowed from the world's most famous capital of gambling and games of chance.
It's called the Monte Carlo method. And at its core, it's really just a clever way of using randomness to get answers to problems that would otherwise be, well, really, really hard to solve. It's like using a kind of controlled chaos to find a single, specific, deterministic answer.
And don't get me wrong, this is way more than just a neat party trick. This method is an absolute powerhouse. It's used everywhere from complex financial modeling to training AIs, and even for mind-bending physics simulations. It's the go-to tool for when the math just gets too messy.
So, how do we wrap our heads around such a huge idea? Well, we're going to use a super simple visual experiment. Let's just build our game board. Okay, first things first, picture a perfect square. Let's say its sides are 2 units long. So what's its area? Easy, right? 2 times 2 is 4. This square is our boundary. It's the known universe for our little experiment. Simple enough? Now let's draw a perfect circle right inside that square. We'll give it a radius of 1. That means it fits perfectly inside, just touching the middle of each of the 4 sides. Now this circle holds a secret we're trying to uncover. And here's where it all comes together. Look at this comparison. For the square, the area is a known quantity. It's just 4. But the circle, well, we know the area formula is pi times the radius squared. And since our radius is 1, the area of the circle is just pi. The very number we're trying to find is literally the area of our target.
Okay, so our board is all set. We have a big area that we know, and inside it, a smaller area that we don't know. Now let's see what happens when we start adding a little bit of that randomness we talked about. So now, let's bring on the chaos. Imagine we just start dropping thousands of tiny little points, like digital rain, all over this entire square. Every single point lands at a completely random spot. Now, what good does that do us?
Well, for every single one of those random points, we ask one simple question. We check its coordinates using the equation for a circle. If x squared plus y squared is less than or equal to 1, then boom, it's a hit. The point landed inside our circle. If it's more than 1, it's miss. That's the only rule we need.
And this right here is the magic moment. It's the key idea. If you drop enough random points, the proportion of points that land inside the circle will start to match the proportion of the circle's area to the square's area. The randomness isn't noise anymore. It's starting to reveal a hidden, precise signal.
So just think about what that means for a second. The ratio of points, something we can just count one by one, is giving us an incredibly accurate estimate for the ratio of the areas. We're using simple counting to figure out something that was supposedly unknown.
So we have this amazing connection between the points we count and the areas we're measuring. Now for the grand finale. Let's do a tiny bit of math and pull pi right out of that random data.
And honestly, the final calculation is so simple, it's beautiful. We start with our main idea. The point ratio is roughly equal to the area ratio. We already know the square's area is 4, so we can just plug that in. Then, with a little high school algebra, we just multiply both sides by 4, and that isolates the area of the circle. And what is the area of the circle? It's pi.
So we run the experiment. We count the number of hits inside the circle. We divide by the total number of points we dropped, and we multiply the whole thing by 4. And out of that beautiful random mess, a number starts to take shape. First 3.1, then 3.14, then 3.141. The more points we add, the closer and closer we get to the true value of pi.
It's just an absolutely incredible result when you stop to think about it. We found one of the most important constants in the universe, using nothing more than a game of chance. Perfect, beautiful order, emerging directly from total randomness.
So yeah, this is an amazing demonstration. But
But let's bring it back home and talk about why this isn't just a cool trick, it's a vital tool in the real world.
So let's just quickly recap this powerful recipe. Step 1. You define a big, easy-to-measure space. Step 2. You make sure your smaller, harder-to-measure target is somewhere inside it. Step 3. You throw a whole bunch of random darts at it. The ratio of hits to total throws gives you the size of your target. It's a fundamental template for solving problems that seem unsolvable.
And that very simple recipe is a cornerstone of so much modern science and tech. Whenever a problem has too many variables or moving parts for a clean equation, like simulating a nuclear chain reaction, figuring out the price of a complex financial instrument, or even training an AI to navigate traffic, the Monte Carlo method gives us a way to get a shockingly accurate answer.
And all of this leaves us with one final, fascinating question to chew on. We just saw randomness pin down one of the most precise constants in mathematics. So it really makes you wonder, what other impossible problems out there are just waiting for the right kind of chaos to come along and solve them?